Hi everyone, I will introduce our work GTP-ViT, efficient vision transformers via graph-based token propagation. This work is collaborated by the University of Queensland, Renmin University of China, and Cyril Data 61. In the past 3 years, vision transformers have achieved outstanding performance on many vision tasks and become the dominant backbone. ViT employs the self-attention mechanism as its core component. It splits an image into several image tokens and then applies the multi-head self-attention on these image tokens. However, the computational complexity of self-attention is quadratic to both the number of image tokens and the number of feature channels. This is why large ViT models are computationally expensive and hard to be deployed on environments with limited computing resources, especially on those edge devices. There have been lots of efforts made to resolve the heavy computational burden of ViTs. Some of them notice the redundancy issue in the image tokens. That is to say, not all the image tokens are necessary for the final prediction. There could be some less informative tokens or similar tokens that can be removed during the inference stage without significantly sacrificing the performance. In general, there are two kinds of solutions to gradually reduce the number of tokens in the self-attention computation as the ViT layer goes deep. One of them is token pruning. Token pruning methods predict the importance score of each token and simply drop those less important tokens. The drawback is obvious. The information of pruned tokens would get lost. So token pruning methods usually need fine-tuning or retraining to be effective. The other one is the token merging method. Instead of simply removing the tokens, token merging method first identify the most similar token pairs and then average them. However, the token matching process is somehow inefficient. It needs to compute the pairwise cosine similarities among tokens in each layer. Therefore, we raise two research questions: how to effectively balance the model efficiency and the information preservation for ViT models, and how to enhance the efficiency of pre-trained ViT models while achieving minimal performance drop without fine-tuning or retraining. And we will define the problem of token removal and information preservation as a token summarization task, where remaining tokens encapsulate the information of the removed ones. To address the challenge of existing methods, we propose the graph-based token propagation for efficient ViT. Here's the overview of our method. There are three major components in our solution. We first generate a token graph for the image tokens before sending them to the backbone. We add edges between the spatially and semantically connected image tokens. And this graph will be used for the subsequent token propagation in each layer. It is worth mentioning that the token graph is only generated once before the transformer layers, so that we avoid repeated graph generation and cosine similarity computation in each layer. We then propose an efficient and effective token selection strategy to select tokens after each multi-head self-attention layer. We focus on two factors to determine the importance of each token. One of them is the regeneration difficulty. As we know, the attention map is used to linearly aggregate the tokens, and the attention weight represents the importance or percentage of each token in the aggregation. As a result, if the attention value of one token to itself is smaller, then this token is mainly aggregated by the other tokens and is less important. These less important tokens can be dropped since they are more easily to be regenerated by the other tokens, and their information is less significant in token summarization results. The other one is the broadcasting ability. We measure the extent that a token contributes to the other tokens. If a token greatly contributes to the other tokens in the aggregation, then this token is important for the token summarization. Unlike the existing methods, our token selection strategy does not need the special class token nor additional components, and we do not need to compute the similarities. It is efficient, effective, and generic. After selecting those less significant tokens, we distribute the information to their kept neighbors on the token graph. We first extract the edges from removed tokens to the remaining tokens. And then we propagate the tokens based on the graph. This process is similar to the graph convolution, but since we only propagate a small number of tokens in each layer, for example, 8 tokens per layer, the propagation graph here is very sparse and the computational complexity is negligible. For more implementation details, please refer to our paper. We have conducted extensive experiments to demonstrate the effectiveness of our methods. All our experiments performed on the ImageNet 1K dataset. We report the results of our method without fine-tuning by default. We choose DIT and LVVIT family as the VIT backbones, which are common backbones for the methods in this area. When the number of propagated tokens per layer is 8, our GTP-ViT achieves 25% real speedup and 26% fewer computational complexity with an insignificant top 1 accuracy decrease of merely 0.3%. And we get very similar results on the other backbones. We would like to emphasize again that all these results are achieved without fine-tuning. We then compare with the state-of-the-art methods on similar computational complexities. Here we visualize the comparisons. The red lines in the figures represent for our method. It is obvious that our GTP-ViT achieves the best trade-off between speed and accuracy. And only token merging and our GTP-ViT can work on ViTs without fine-tuning. The other methods all suffer significant performance decrease when more tokens are removed. We also validate our method on various ViT backbones, including ViT base patch 8, which has 785 tokens instead of merely 197 tokens as a normal ViT has. We also test our method on ViT using global average pooling, which does not have the class token. And we test on larger ViT models such as ViT large and EVA large. Our method outperforms the state-of-the-art token merging method on all these backbones. These experiment results demonstrate that our GTP-ViT is universal and robust. We also visualize the token selection results of our method. Unlike the existing token pruning methods that focus primarily on eliminating less significant background tokens, GTP-ViT ensures that a certain retention of the background tokens will be remained, thereby providing a summarized representation of the original image. We evaluate the token selection methods and also compare with the other token selection strategies. Our token selection strategy is more robust with different number of propagated tokens per layer and achieves the best performance. Finally, we analyze the effectiveness of our method from the graph aspect. We noticed that existing token pruning methods lead to over-smoothing problem, that their remaining tokens tend to be very similar to each other. As a result, the deeper layers of a ViT can hardly learn useful image features, and this is why they need to fine-tune the backbone after pruning. And we also find that preserving token information can relieve such an over-smoothing problem. In the figures below, our method is significantly anti-over-smoothing, which might be the reason why graph-based token propagation works. There are more experimental results and analysis in our main paper and appendix that are not covered in this presentation due to time limits. We recommend you to read our paper. Here's the contribution of our work. We propose a novel and efficient token selection strategy, and we propose a graph-based token propagation method to summarize all the image tokens. Our method enhances the efficiency of vision transformers without the need of retraining or fine-tuning. That's all for our work. Thank you.